In the quiet, cold expanse of the Orion Cygnus arm, suspended within a spiral galaxy of 100 billion suns, a single star system follows its prescribed, elliptical path. It is a system unremarkable in its gross architecture, a G-type main sequence star, a collection of rocky inner worlds, and a retinue of gas and ice giants patrolling the outer darkness. Yet, within this commonplace arrangement, one planet occupies a position of extraordinary improbability. It moves within a zone of temperate radiation, a habitable band barely 1% of the distance between its sun and the next nearest star. But its stability is not a simple matter of location. Farther out, a behemoth of hydrogen and helium, a planet more than 300 times the mass of this world, circles in a near-perfect orbit, its immense gravity acting as a celestial shield, sweeping the inner system clear of rogue comets and asteroids, deflecting a fusillade of cosmic debris that would otherwise render the inner world sterile. Closer still, orbiting the planet itself, is a moon of anomalous size, a companion so large relative to its primary that it seems more a binary partner than a satellite. This moon's gravitational tether is a steadying hand, preventing the planet's axis of rotation from tumbling chaotically over geological timescales, thereby locking its climate into a rhythm of predictable seasons, a gentle, metronomic pulse against which the first stirrings of complexity could measure themselves. The parameters appear finely tuned, the initial conditions set with a precision that borders on the deliberate, as if this small, blue world were not an accident of accretion, but a carefully prepared crucible, an isolated laboratory designed for a single, long-form experiment. Beneath the thin skin of its atmosphere, the planet itself is a dynamic engine, a body kept alive by a core of immense heat. This residual warmth from its violent formation, sustained by the slow decay of radioactive elements, drives a process of planetary renewal on a scale of hundreds of millions of years. The solid mantle, behaving like a viscous fluid over eons, churns in vast, slow-moving convection cells, dragging the brittle crust along with it. This is the mechanism of plate tectonics, a geological feature whose significance transcends the mere shifting of continents. As slabs of oceanic crust are forced to dive beneath continental margins in a process known as subduction, they carry with them water and carbon, sequestered from the surface. Deep within the mantle, this material is heated, metamorphosed, and eventually returned to the surface through volcanism. This global cycle acts as a planetary thermostat, regulating the concentration of greenhouse gases in the atmosphere, preventing the world from freezing into a permanent ice age or boiling away into a runaway greenhouse state. The constant rifting, subducting, and colliding of tectonic plates creates a breathtaking diversity of chemical and physical environments, deep-sea hydrothermal vents spewing mineral-rich superheated water, shallow continental shelves bathed in sunlight, towering mountain ranges exposing new rock to weathering, and vast basins where sediments can accumulate for ages. This restless geology is not a flaw in the system, it is the system's primary engine of creation and regulation, a mechanism for continuously supplying raw materials, generating chemical gradients, and creating isolated niches where novel solutions to the problem of existence can be tested and refined. The stage for the experiment is not static, it is alive, constantly reshaping itself to pose new questions and elicit new responses. The crucible is prepared, the engine is running, but the experiment requires a medium, a universal solvent in which the chemistry of life can unfold. On this world, that medium is water, a molecule of deceptive simplicity and profound anomaly. In its liquid state, it covers more than 70% of the planet's surface, a vast thermal reservoir whose high specific heat capacity allows it to absorb and release enormous amounts of solar energy with only minor changes in its own temperature. This property moderates the planet's climate, softening the thermal extremes between day and night, between summer and winter, creating a stable thermal envelope for life to exist within. Its power as a solvent, born from the polarity of its hydrogen-oxygen bonds, allows it to dissolve salts and minerals from rock, transporting nutrients across continents and through the tissues of living things, creating the rich chemical broth of the oceans. But its most critical anomaly is revealed when it freezes. Unlike almost any other substance, water becomes less dense as it solidifies, causing its solid form, ice, to float. This simple fact has world-altering consequences. In the polar regions, a floating cap of ice forms each winter, insulating the liquid water below from the killing cold of the air, allowing marine ecosystems to persist in a state of suspended animation until the return of the sun. Without this property, ice would sink, and over millennia, the planet's oceans would freeze solid from the bottom up, entombing the world in a permanent, lifeless sheath of ice. This unique molecular behavior, an exception to the ordinary rules of physics, is a fundamental prerequisite for the planet's long-term habitability, a feature so crucial it appears less like a fortunate quirk and more like a non-negotiable design specification for the liquid medium in which the experiment is to be conducted. Within this aqueous, geologically active environment, the trial's first and most crucial phase began, the transition from non-living chemistry to self-perpetuating biology. At the bottom of the primordial oceans, where tectonic plates spread apart, hydrothermal vents discharged a torrent of chemical energy into the cold, dark water. Here, in the steep gradients between the alkaline, hydrogen-rich vent fluid and the acidic, carbon dioxide-rich seawater, a natural energy potential existed, a planetary-scale battery. The porous rock of the vent structures, honeycombed with iron sulfide compartments, acted as a scaffold, concentrating organic molecules and providing catalytic surfaces for their assembly into more complex polymers. Within these microscopic chambers, a precursor to metabolism may have taken hold, a cascade of chemical reactions powered by the planet's own geothermal energy. Elsewhere, in shallow, sun-drenched lagoons, cycles of evaporation and rehydration could have driven the polymerization of amino acids and nucleotides on the surfaces of clay minerals, their crystalline structures acting as templates for organization. From this planetary-scale chemical experimentation, a molecule of profound capability emerged. It was not yet life, but it was the blueprint for it, a self-replicating polymer, perhaps a strand of ribonucleic acid, or RNA, capable of both storing information and catalyzing its own duplication. This was the inflection point, the moment the system achieved a new state of being. The inanimate had, through a series of contingent steps, given rise to the animate. The trial had achieved its first metric of success, the initiation of an evolutionary process, a chain reaction of replication, mutation, and selection that would, from this point forward, begin to transform the planet in its own image. For nearly 2 billion years, the experiment proceeded in a quiet, microbial phase. Life was confined to the oceans, dominated by single-celled, anaerobic organisms that thrived in an atmosphere devoid of free oxygen. But within this seeming stasis, a revolutionary innovation was taking hold. A new lineage of bacteria, the cyanobacteria, had developed a radical new method for harnessing the energy of the sun. Through photosynthesis, they learned to split the abundant water molecule, releasing its hydrogen to build organic matter and discarding its oxygen as a waste product. For hundreds of millions of years, this oxygen was immediately consumed, reacting with dissolved iron in the oceans to form vast deposits of banded iron formations, which now lie as silent, rusted testaments to this planetary transformation. But eventually, the oceanic sinks were saturated. The waste gas, a corrosive, highly reactive element toxic to the anaerobic life that had dominated the world, began to accumulate, first in the water and then, catastrophically, in the atmosphere. This was the Great Oxidation Event, the planet's first self-induced global crisis. It was a pollution event on a scale unimaginable, triggering a mass extinction of the old anaerobic guard and fundamentally rewriting the rules of biochemistry. It appears as a great filter, a severe stress test for the biosphere. Could the system survive its own success? The answer was a resounding, transformative yes. Life adapted. New metabolic pathways evolved to not only tolerate oxygen but to harness its potent reactive power, unlocking vastly more energy from organic molecules than was ever possible before. The trial had not failed, it had escalated, introducing a high-energy fuel that would power the next great leap in biological complexity. The newly oxygenated world provided the energetic landscape for the next major breakthrough, an event that would occur only once in the planet's 4 billion-year history of life. It was not a new species, but a new kind of cell, a quantum leap in internal architecture and complexity. The eukaryotic cell was born not from gradual mutation, but from a collaboration, a series of mergers between ancient prokaryotic cells. In an act of endosymbiosis, one single-celled organism engulfed another, not to consume it, but to incorporate it. A small, oxygen-breathing bacterium, once ingested, was transformed into a permanent internal partner, a power plant that would become the mitochondrion, supplying its host cell with abundant energy in exchange for shelter and nutrients. In a separate, later event, a photosynthetic cyanobacterium was similarly engulfed by one of these new cells, becoming the chloroplast, a tiny, internal solar panel that would give rise to the entire kingdom of plants. This new type of cell was a marvel of modular design and compartmentalization. It possessed a nucleus to protect its genetic material, an internal scaffolding system for structure and transport, and these symbiotic power packs that provided it with an energy budget orders of magnitude greater than any prokaryote. This innovation was the key that unlocked the door to multicellularity. With energy to spare and a new system for organizing genetic information, cells could begin to specialize, to cooperate, to build large, complex, three-dimensional bodies. This was not merely another step in the evolutionary pathway, it was the creation of an entirely new platform for being, a foundational shift that enabled the construction of fungi, plants, and animals. The experiment was now testing for the emergence of cooperative systems and hierarchical organization. With the eukaryotic platform established and the oceans rich in oxygen, the stage was set for another explosive acceleration. For 3 billion years, life had been largely microbial and asexual, with organisms reproducing through simple cell division, passing on their genetic material with near-perfect fidelity. Change occurred slowly, through random mutation. But then, a new process arose, sexual reproduction. The shuffling of genes from two parents to create a genetically unique offspring was a revolutionary invention. It was an engine for generating variation, the raw material for natural selection, at a rate previously unimaginable. This new capacity for rapid innovation, coupled with the high-energy metabolism afforded by oxygen and the complex body plans made possible by eukaryotic cells, culminated in a frenzy of creation known as the Cambrian explosion. Over a period of just 10 to 20 million years, a geological instant, the biosphere erupted in a riot of anatomical experimentation. The first recognizable ancestors of nearly all modern animal phyla appeared in the fossil record. Organisms developed shells and exoskeletons, limbs and antennae, compound eyes and complex nervous systems. Predators and prey engaged in an evolutionary arms race, driving the development of ever more sophisticated means of attack and defense. It was as if a key had been turned, and a silent, waiting factory had roared to life, churning out an astonishing diversity of forms. The trial was no longer simply about persistence, it was now a test of creative potential, a measure of how quickly and diversely the system could populate the available ecological space with new and complex solutions for survival. The history of this planetary experiment is not a smooth, linear progression toward greater complexity. It is a story punctuated by catastrophic interruptions, by periodic, system-wide resets that pruned the tree of life back to its trunk. At least 5 times, the biosphere has been convulsed by mass extinction events, episodes of such profound environmental upheaval that more than 75% of all species vanished in a geological moment. The most severe of these, the Permian-Triassic extinction, known as the Great Dying, saw the demise of up to 96% of marine species and 70% of terrestrial vertebrate species. The cause appears to have been a perfect storm of geological calamity. Massive volcanic eruptions in Siberia released colossal volumes of carbon dioxide and methane, triggering runaway global warming, ocean acidification, and widespread anoxia. Another event, the Cretaceous-Paleogene extinction, was triggered by an external shock, the impact of a 10-kilometer-wide asteroid that struck the planet with the force of billions of atomic bombs, shrouding the globe in a pall of dust and smoke that blocked out the sun. From the perspective of the organisms living through them, these were incomprehensible apocalypses. But from the perspective of the long-form experiment, they serve a different function. They act as crucible filters, testing for ultimate resilience. They clear the ecological stage of dominant, entrenched incumbents, creating vast evolutionary opportunities for the humble and the adaptable who survive. The mammals, small, nocturnal creatures that had lived in the shadow of the dinosaurs for 100 million years, were beneficiaries of just such a reset. The extinctions are not failures of the system, but integral parts of its dynamic, a mechanism for ensuring that no single solution becomes permanently locked in, ensuring that the trial remains open to novelty. Following the most recent of these great purges, the experiment entered a new and perhaps final phase. Among the surviving mammals, a lineage of primates developed a unique set of adaptations. Bipedal locomotion freed their hands for manipulation. An opposable thumb allowed for a precision grip. But the most significant development occurred within the skull. The brain, and particularly the neocortex, began to expand at an unprecedented rate. This metabolically expensive organ, consuming up to 20% of the body's energy budget, conferred a powerful new capacity, abstract thought. These creatures developed language, a system of symbolic communication that allowed for the transmission of complex information across generations, creating a cumulative culture that evolved far faster than their genes. They learned to control fire, to fashion tools of stone and bone, and to domesticate other species. They developed a model of the world, a consciousness of self, and an awareness of time, past, present, and future. This was the introduction of the cognitive variable, a form of life capable of understanding the very processes that created it. This new entity, humanity, was no longer just a subject within the experiment, it was a participant, capable of observing, analyzing, and, for the first time, consciously manipulating the planetary system itself. The emergence of self-awareness on this planet marks the trial's most complex and perhaps most perilous achievement. A system designed to produce novelty had produced a novelty that could, in turn, redesign the system. The present epoch, which some have termed the Anthropocene, represents the culmination of this cognitive development. The conscious species has become a geological force in its own right, its collective activities now the dominant driver of change on the planet. Its industrial processes are altering the chemical composition of the atmosphere and oceans at a rate far exceeding the natural regulatory cycles of plate tectonics, pushing the climate system toward a new, hotter state. Its agricultural and urban expansion has fragmented and destroyed habitats, triggering a new mass extinction event, a biodiversity crisis entirely of its own making. The experiment has produced a creature of immense power, but it remains an open question whether that power is coupled with sufficient wisdom and foresight. Is this the final test of the trial? Can a species that has attained planetary scale influence learn to manage its own impact, to integrate itself into the biosphere's metabolism in a sustainable way, thereby achieving a new and stable form of global equilibrium? Or is consciousness itself a great filter, a fatal adaptation that inevitably leads a species to exhaust its planetary host before it can achieve the maturity required for long-term survival? From a great distance, the planet remains a single, luminous point of blue and white, a shimmering jewel against the black velvet of space. The experiment continues. The data is still being gathered. The outcome remains unwritten, observed in patient silence from across the unfathomable gulfs of time and space, a single trial running its course in a quiet corner of the cosmos.